Hello everyone, welcome to our final year project demonstration in the Design Project module in semesters 7 and 8. So, let's get started with a brief introduction to the project. First, let's see what this frequency response test is. This is an alternative testing approach that can be used to estimate the dynamic parameters of a synchronous machine accurately, rather than using conventional tests like sudden three-phase short circuit tests. When it comes to large synchronous machines, this test is really essential to estimate dynamic parameters, because it is difficult and too risky to conduct the short circuit test on such large machines. To conduct this test on a given synchronous machine, there should be a voltage source that is capable to deliver adjustable frequency and adjustable RMS sinusoidal outputs. This project is about designing this voltage source as a single-phase inverter which is suitable to conduct this frequency response test. Now you have a clear understanding about what this project is. Let's have a look at the design and simulation results of the proposed inverter. This is the power circuit of the proposed inverter. In here, full bridge topology was used with IGBTs as switching devices and unipolar sinusoidal PWM switching was selected to drive them individually. Since this is a PWM inverter, it produces pulsed output. This passive LC filter is there to separate the fundamental. Commercially available inverters mostly deliver a sinusoidal output having fixed frequency and fixed RMS. But, this inverter design is not something like that. Our inverter can deliver variable frequency and variable RMS sinusoidal outputs. Therefore, this is not an ordinary inverter design at all. Now, let's have a look at how this inverter performs to deliver required outputs. It should be able to deliver adjustable frequency outputs in a specified range. This is how it satisfies this requirement. In this scenario, model was tested many times under different frequencies to check whether it performs satisfactorily. In addition to the frequency adjustability, output RMS should also be adjustable. This is how inverter delivers variable RMS outputs at a given frequency. If the field winding of the machine under test is not accessible, we can give required field excitation to establish the field flux through this inverter itself. This is an advanced feature of this inverter, and it is done by superimposing a DC component together with AC output. These simulation results illustrate how the designed inverter delivers DC shifted sinusoidal outputs. With the simulation results, now it is clear how our inverter design performs well to meet the requirements. To deliver these outputs in real time, we have to correctly switch the IGBTs in the inverter. To generate correct switching signals, we have developed this model in the MATLAB Simulink environment. Without limiting to just simulations, we put one step ahead to implement this model physically. Implementation of this model with real hardware was the most difficult and crucial part of this project. Now, let's go to the Power Systems lab to see how that model was physically implemented. This is the complete arrangement of the control circuitry of the inverter. This is where all the controls are done, in order to deliver required output. These are the different subcircuits. Let's see how they function. This is the DC power supply that we have used to power up all circuits. It has two isolated channels. 12-volt DC output is taken from this supply. Since we have used operational amplifiers to implement this circuit, there should be dual polarity DC supply to power up these op-amps. Therefore, two channels of the power supply were connected in this way. Now, we can take plus 12-volt output from here, minus 12-volt output from here, and common ground from here. Here we have multiple circuits to power up. Therefore, we implemented this DC rail to get multiple power outputs. This is the carrier signal generator circuit to generate 10 kHz carrier. When we power up this circuit, it generates decent triangular signal as displayed on the oscilloscope. Here you can see, its frequency is 10 kHz. This is the reference signal generator. Now let's look at how this circuit works. This is a non-inverting amplifier, summing amplifier, inverting amplifier, and this is a buck converter. This block diagram shows how these circuits are interconnected to generate required outputs. Now let's see the output of this circuit. Top waveform is the positive reference signal and bottom waveform is the negative reference signal. When we adjust the amplitudes of reference signals, modulation depth changes. As a result, RMS value of the output voltage of the inverter will be changed accordingly. This is how voltage variability of this inverter is achieved. Our inverter design can produce DC shifted sinusoidal outputs in case of the field winding of the machine is not accessible. This DC component is used to produce required field excitation through the inverter itself. To implement this function, we have used this buck converter module to provide adjustable DC signal. This is the LM2596 buck converter module. After power up, this is the input voltage to the module. This is the output voltage. This is the potentiometer, to change the operating duty factor of the converter. Now let's see how this circuit do its job. Oscilloscope shows the positive reference signal without having a DC offset. Now you can see, when we adjust the potentiometer setting, reference signal is getting DC shifted. When we do this adjustment, inverter output also gets DC shifted. This is how we implement a control action, to give a required DC offset to the inverter output. Now, let's look at PWM switching signal generator. This is where all switching signals are processed to generate correct switching signals. This circuit takes carrier signal from here, positive reference signal from here, and negative reference signal from here. These signals are compared by these comparator ICs and generate PWM switching signals accordingly. This is where for switching signals are taken out to drive individual IGBTs. Now you can see on the oscilloscope switching signals generated by this circuit. This is the end of our project demonstration. Thanks for watching.